Welcome, anatomy students, to part 2 of chapter 3. I'm going to share my screen with you, and let's cover part 2 of the tissue level of organization. When we left off, we were just starting to talk about connective tissue. In part 1, we went through epithelial tissue, membranes, secretory tissue, and now we want to dive into connective tissue. So what is connective tissue? Well, we are going to distinguish the different types of connective tissue being proper, supportive, and fluid. We're also going to go over the functions. We're going to do functions. Connective tissue is a little bit interesting, very diverse. And I think when you look at the slides in lab, you're going to be very surprised at just the variety. So let's look at the connective tissue. There's structural characteristics. These connective cells are dispersed in what we call a matrix. This is the ground substance, or kind of the, it's the matrix that they are living in. We'll take a look at that, right? So there's a large amount of this ground substance. They are primarily protein fibers that intersperse in that ground substance, and they have a real variety of how they're organized. So what is the function of these connective tissues? Mainly to support the tissues that might be near them, and also connects the tissues and organs, kind of keeps everything held together. Provides a protective function, and also can transport materials. We're going to learn that blood is actually categorized as a connective tissue. So we know that blood has a very specific role, and that is from a bone source. So that's part of why it is a connective tissue. Also, we find that there's some energy storage. Adipose tissue is a connective tissue. So we know fat stores a lot of energy. The embryonic origin of our connective tissues, if you recall from part 1, the mesoderm. This is the middle layer in the embryo as it's differentiating. So how do we classify connective tissues? There's 3 broad categories, and this basically is related to how their matrix, the types of fibers, and how they're arranged in the matrix. Hopefully this will become a little bit more clear. We have connective tissue proper. This comes in both a loose and a dense type of connective tissue. And I think that's a little bit self-explanatory. Loose connective tissue, like you would find under your skin. Dense connective tissue, like you would find in tendons and ligaments. But that's what we would obviously consider connective tissue, right? Then we have supportive connective tissue. This is your cartilage and bone. And from the bone origin, we have a fluid considered a connective tissue, and that's your blood and also your lymph fluids. So those are the 3 categories: our proper connective tissue, our supportive, and our fluid. So let's just take a look. I know, crazy drawing, right? Our proper connective tissue. What is going on in a basic connective tissue? And I just wanted to introduce you to some of the players. So we have this is a cartoon, obviously, but we have some players in here. Primarily the fibroblasts. Those are cells, active cells, fibrous cells. And where are my fibroblasts? Here they are. And you see the fibroblast is identifiable with its nucleus. Adipocytes are fat cells. We have stem cells, the mesenchymal cells, and very importantly, macrophage. Here's a macrophage, the big yellow guy, and also, or pink, up on the top, more of like a scanning electron micrograph. Macrophage is a white blood cell macro, large, phage for phagocytosis, eating. This is an immune system cell that is always on the hunt. It eats bacteria and other debris or cells that it finds in the tissues that it thinks don't really belong there. So they're very important. They move around within the connective tissue. They're not fixed. They can kind of scavenge for any foreign invaders there. We also have another cell of the immune system called a mast cell, and here it is. Those release histamine, and they're very important in the inflammatory process. So like when you get, you have any kind of either an infection or an allergic reaction, think of in the skin how it turns red and puffy. Those are the mast cells releasing histamine, but they're all part of this connective tissue. So lots of cells living in here. And then we have fiber types that are being laid down by these cells. We have collagen fibers. Let's see if I can find a collagen fiber, right? Associated with our fibroblasts. So those are, collagen is a protein and it gives it a lot of strength. We also have elastic fibers in here. And I don't see any specific, those are probably the blue ones. Also reticular fibers. Oh, the blue ones are the reticular fibers. So probably the red ones in here are my elastic fibers. Different protein type fibers and different connective tissues will have different amounts of them. This gives your connective tissue elasticity and strength. I always think of them as like little rubber band fibers in there. So if you think about how much, for instance, your skin can move and stretch and stay with the underlying tissues, that's because it's attached by these connective tissues. So that's just an overall look. Here's another similar picture. The one on the left is a cartoon. The one on the right is showing you, let's see, it's a little bit hard to see in here, but we've got some fat cells. We have some fibrocytes. So this is kind of a loose type of a tissue. So our first proper connective tissue we call loose connective tissue or areolar tissue. And you're going to look at this under the microscope and be able to identify the different fiber types and cell types. So this is the type of tissue that binds underlying organs to the skin and to each other. It's a fairly delicate, if you will. It's easy to disturb. So we all know about adipose tissue, right? Adipose tissue provides a protective cushion, also insulation, but as you know, it's also an energy store. So it's a very loose tissue, easily disrupted, but these cells just love to take in and store fat. That's more loose connective tissue, more adipose tissue. Okay, this is tissue called reticular. And you see these reticular fibers in here. We find these fibers in glands oftentimes. This looks to me like a lymph node, and this is kind of helping to hold the glandular cells together. And we have our fibrous connective tissues. So tendons, remember, connect muscle to bone. For instance, your huge Achilles tendon that connects the back of your gastrocnemius, your calf, to your calcaneus. So your heel is actually attached to your calf muscle, which is how you walk, right? But then bone is connected to bone with similar fibrous connective tissue, but that's a ligament. So you definitely in this class want to remember the difference between tendons and ligaments. Tendon is muscle to bone, ligament bone to bone. Similar in construction, but different in function. So this is just kind of a look at some of that tissue, right? So here we have some of the ligaments in the knee connecting the knee bones together, right? You probably know about your lateral your lateral and collateral. Where's the one everybody injures? The anterior cruciate, the ACL. That's the one everybody likes to tear and get surgery on, right? So this is what that dense fiber looks like. Closely packed fibers, and that's why we call it dense fibrous, very strong. So here's a regular dense, where we have a regular layering of our collagen fibers, and here you see the fibroblast nuclei. And we also have irregular dense, where it's not layered as cleanly. And then we see some of our collagen fibers are more in bundles, and we'll have elastic fibers interspersed here. So let's think about our supportive connective tissues. You're probably very familiar with bone, but also cartilage, which is kind of like a cartilage can be converted into bone, right? Both of them are based on cells. In the case of cartilage, we call them chondrocytes, and in the case of bone, we call them osteocytes. These are cells that live in spaces called lacuna. They are within the matrix of either the bone or the cartilage. So cartilage we would consider a semi-solid matrix laid down by chondrocytes. It tends to be avascular, which actually is one of the properties of cartilage. Doesn't heal very quickly. If you have cartilage damage, it takes more time to heal it because there's not as much blood supply there. Bone is a very solid matrix. You know that bone contains a lot of calcium, phosphorus, it's mineralized, at least the compact bone is mineralized. It's laid down by osteocytes, which also live in their little spaces called lacuna, but it is a vascular tissue. And when we get into studying the bone structure, there's a lot going on there. So let's look at cartilage. You know, cartilage in your ear, for instance. This is made up of chondrocytes, which are the cells in the space around the cell known as the lacuna. And here we have some different types of cartilage that we're going to explore in the lab. Cartilage that you would find in association with your bones, hyaline cartilage, and here we have the chondrocytes and the cartilage matrix. We also have fibrocartilage, a little bit more collagen fibers in here. And we also have an elastic cartilage. And we'll talk about specifically where these are in a moment. So here's your hyaline cartilage. And this is a classic picture. I definitely want you to be able to recognize it. This is actually, I believe, from a tracheal ring. You would also find this type of cartilage covering the ends of the joints, or ends of the bone in the joint. So you would have at the end of a long bone covered in this type of cartilage. In the ear and also in our voice box, the larynx, we have this elastic cartilage. So, you know, if you feel your ear is much more elastic fibers in there. And the fibrocartilage is a very tough shock absorbing cartilage that lives in your discs, these intervertebral discs. You've heard of, you know, if somebody blows out a disc, that's exactly what they're talking about. Between the vertebrae of your your vertebral column, you have those elastic fibrocartilage discs. So let's move to bone. You may remember in your previous studies of bone The compact bone is arranged in these circular structures that we call osteons. Within each of the osteons is a central canal. This is where blood vessels would be coming in and throughout the bone. And you'll also notice that these osteons have layers. They're concentric layers, almost like the layers on a tree, like you know how bark grows in layers. Well, your bone osteons also grow in layers, and these are known as lamellae. The little dark spots that you see there are actually the bone cells, the osteocytes, and they live within a space. When you zoom in a little closer, the space around them is known as the lacuna. Now, this is compact bone. You would find this around the edge of the bone and also at both ends of your long bone. But remember, the red bone marrow, red bone marrow, the spongy bone has a little bit different structure where you have these trabeculae that come into the bone, but there's a lot more open space, which is full of red marrow. And this is actually where your red blood cells, well, all of your blood cells are made. So let's look at the blood a little bit. We consider that a fluid connective tissue. And so the blood cells circulate in what we would consider a liquid extracellular matrix. I know that seems a little strange. It's there to transport material. We have blood and we have lymph. So there's blood. You've looked at that before. In the lab, we looked at the red blood cells, also known as erythrocytes. These are very specialized. They have no nucleus anymore. They are specialized to carry oxygen, carbon dioxide, but they bring oxygen to the tissues. Also within the blood, we have white blood cells, and there's a whole population of these. Lymphocytes specifically are your B and T cells that live in the lymph nodes primarily, but we also have other white blood cells, leukocytes, and we also have platelets, which are not shown here, but we'll get to see those in the lab. So how are these connective tissues organized? There's several layers that help us to, I guess, hold the tissues together, right? We have our superficial fascia, deep fascia, and subserous fascia. What am I talking about? Let's take a look. So here is a cartoon. The outer portion on the left would be the skin. Directly under the skin would be your superficial fascia. Then we would get to deep fascia, which you see sort of surrounds the muscle layers and within, kind of holding the muscle. This is part of your muscle to skin connection. And also you see connections to the bone here. And then around an organ like the lung, we're going to have the subserous fascia. So those are just different connective layers that kind of help hold us together. So let's take a look at our muscle tissues. So we just did connective tissue, now the muscle tissue. You'll recall that there are 3 types of muscle tissue. We're going to look at the function of each of those muscle tissues and how they're different, and how muscle can enable motion. Remember when you studied the sliding filament model for our striated muscle? That's a very important concept to understand. So our muscle types. We have smooth muscle, cardiac muscle, and skeletal muscle. They are excitable tissues and they can respond to stimuli. They can contract basically and shorten. So muscle tissue can either shorten in a very organized fashion, the striated muscle like cardiac and skeletal, or in a little bit less formal fashion, but still with contractile fibers, the smooth muscle. So the ability to contract can be under voluntary control or involuntary control. You can decide to contract your bicep and move your arm, right? But can you decide to contract your small intestine? No, probably not. Can you choose to contract your bladder? Unlikely. And what about your heart? Even though it is a striated muscle, you don't have voluntary control over that. So that's an important characteristic that we want to keep in mind when we talk about these muscles. So we can identify these types according to their structure and what they do: skeletal, cardiac, and smooth. Under the microscope, they look quite different, and you definitely want to learn how to identify these guys. So this top one, which one is that? Skeletal, cardiac, or smooth muscle? And how would we know that? Well, at this magnification and without looking a little bit closer, you might have a little bit of trouble. But you see how these long fibers are arranged in nice cylinders? And there's lots of nuclei that are right on the periphery of those cylinders. If we could look in a little closer, you'd probably see the striations. So this is skeletal muscle on the top. If we come down a little bit further, again, little tricky to tell right here, but these branching type of fibers, if we could zoom in on them, they're also striated. That's going to be cardiac muscle. Now, these cardiac muscle fibers, you notice how there's little spaces between them. And I think if we zoom in, we would also see what are called intercalated discs. That allows these muscles cells to talk to one another. But we have one nuclei per cell, still striated, but they're more branching. Here in the middle, we see kind of the cells sort of together in a smooth layer. That is your smooth muscle. So how about skeletal muscle? This is used to attach, it attaches to bones. It's under voluntary control and it is striated. So this is what allows for movement, facial expressions, right? The ability to move your body, just everything we think of as how we move. This is done with skeletal muscle. Cardiac muscle is really interesting because it's electrical. It's involuntary, but it's striated, and it has specialized cells we call cardiomyocytes, and they are attached to one another so that you have an electrical signal that starts up here at the top of the right atria and travels down throughout the heart to cause contraction. But the cells of the heart itself, the muscle cells of the heart, carry that electrical signal. These guys are connected by gap junctions and can electrically talk to one another to coordinate that pumping action. So here's a little closer look. If we zoom in on a cardiac muscle cell, you see how they're branching. They have a nucleus, but right here we have this connection between the cells. These are called intercalated discs. And what they do is they have gap junctions, which allow for, I'm trying to look here, zoom. We can send sodium ions or other ions right from one cell to another. So we get basically an electrical event that goes right from one cell to another. And there's some of your adhesion junctions that are just holding the tissue together. What about smooth muscle? This is involuntary. It is not striated. This is what contracts our digestive, urinary, and reproductive systems, um, along with airways, arteries, changes the shape of the lens in your eyes, causes the hair to stand up on your skin. There's a lot of involuntary contraction that's done by smooth muscle tissue. So on to nerves. Nervous tissue, we're going to identify cells and also how it basically works. So nervous tissue is excitable, right? It can send and receive electrochemical signals. We're basically, when we look at a slide of nervous tissue, we're going to see two cell types, neurons and neuroglia cells. So here's the neuron, classical neuron that you're used to seeing with a cell body, dendrites that are connected to other cells, other neurons, and then the long axon that propagates the nerve signal to the axon terminals, which are going to then connect to another nerve cell, and kind of on it goes. Around these neurons are these neuroglial cells. These are what we would sometimes call nurse cells. They're supporting cells. They help to bring nutrients to the neurons. So here is kind of our cartoon. Here's a neuron with the cell body, nucleus, a little finger-like dendrites reaching out. And you remember down the axon, we have these fat wrapping myelin sheath. And where's our little, I don't see the neuroglia in here, but here are some neurons you could recognize in this neural tissue. They always have kind of that star-shaped appearance. You may have also seen these in your multipolar neurons slides from week 1. Your classic neuron, you should be able to draw that in your sleep. You will be able to after this class. So how do we deal with tissue injury and aging? So their tissue injury is associated with inflammation. There are a number of body responses that we're going to talk about, and then how tissue is repaired. And what is the effect of aging on tissue? We can even get into a little bit of how cancer affects tissue. So when you injure yourself, inflammation is the standard initial response, right? This is those mast cells releasing histamine, calling on the immune system to come. It's going to bring the repair systems and the immune system to the site of injury. Sometimes we have death of the cells around the site of injury. This is called necrosis, right? This can happen when blood flow is cut off. This also happens in the case of diabetes, where proper circulation isn't occurring in a tissue, and you can have cell death. This is going to cause inflammation because it's going to alert the immune system. There's another kind of cell death called apoptosis, where cells are kind of like their clock is up. They die on kind of a scheduled death. And this does not cause inflammation. Like your skin cells naturally die on a clock. So what does it look like when we have inflammation? You kind of know this intuitively. Redness, swelling, pain, and heat. So let's look at how these injuries are going to heal, right? So here's an injury that has breached the epidermis into the dermis. And what's actually going on here, right? This injury has released inflammatory chemicals or histamines. The mast cells are going to release that. And what's going to happen, those go into the bloodstream and alert your white blood cells, which were probably in the lymph nodes, right? But here they are, they're now alerted and they're going to come to the site of injury. So inflammation will actually help bring additional blood flow, bring additional immune system, also helps the blood vessels to open up a little bit so that these cells can get in here. While we are alerting the immune system, we also have clotting factors so that if there's any bleeding happening, we can bleed and clot and form a scab. Okay, so very shortly, we're going to have the white blood cells, including those macrophages, coming into the area, and they're going to be cleaning up the debris. Now we have kind of a clot in here. Where's my clot? This clot is being resolved into what we call granulation tissue. This is the first restorative tissue trying to come back. It doesn't have all the perfect form, but it's doing some repair, and then it allows the vascular supply to be restored. As the epithelium here is repairing and being restored, we then have some contraction of the area, and whatever granular tissue cannot be sort of remodeled and restored is going to kind of form into a scar. So initially, that granular tissue is very important for sort of filling in the hole and bringing vascular system in, but over time that can actually just not be resolved and end up in a scar. So that's kind of tissue healing at a glance, right? So as you review chapter 3, remember we're looking for four types of tissue. In the first slide series, I went over the epithelial tissues. In this section, we went over connective, muscle, and nervous tissue with a little bit here on wound healing. So those are all the tissues you're going to look at in the lab, and you should become very familiar with what they look like and what their functions are. So we'll see you in lab.